I'll be telling you about the modeling of CMOS cells. In my talk, I'll talk about first the key parameters and properties of CMOS, and then we'll talk about modeling of CMOS cells and arrays for optimal designs. And I'll be talking about interesting effects due to interactions between the cells of an array. And finally, we'll find out if we can use these interesting effects as high-Q resonances in immersion for sensor applications. So this is the, as Pierre showed, this is a typical CMOS cross-section where you have a plate made from silicon or some other material that vibrates due to the electric force in the vacuum between the top plate and the bottom. The advantages of CMOS, inherently very low Q, that means very wide bandwidth. That also means that very good time resolution for imaging applications. And the efficiency of a CMOS is also very good, 100%, close to 100%. And because it's manufactured using photolithography, no limitation for array geometries. And it's also very suitable for high-frequency applications. And also it's very possible to obtain high pressures. So in this is the CMOS cross-section where the top plate is moving between these two. There is a collapse limit for static, but in the dynamic case, it can move actually beyond that point, so you can get actually very high powers. And the electrostatic Coulomb force between the top plate and the bottom electrode, as I mentioned, generates acoustic transduction. The key parameters of a CMOS cell is the radius of the plate, the thickness of the plate, and the gap height. I'll just be talking about these three properties. And the mechanical resonance of the plate determines the lowest operation frequency, typically. If you look at the collapse voltage, this is the voltage beyond which the plate will collapse to the bottom. So typically you want to operate below this value. And collapse voltage is proportional to the thickness to the 3/2 power. And also it's proportional to the gap to the 3/2 power. And it's proportional to, inversely proportional to the square of the radius of the cell. So if you quadruple the thickness, the area, the radius should be increased by 2, factor 2, and at the same time, I should decrease the gap by about 1.5 times to keep the collapse voltage the same. So basic properties again, force is proportional to, from Coulomb's law, of course the excitation voltage squared, the radius squared, and the gap squared, inversely proportional to the gap squared. So for the same voltage, a smaller gap gives a higher force. And collapse voltage is proportional to these quantities. And the resonance frequency is proportional to Tm over A squared. So all these things should be handled at the same time during a typical design. So if you want to keep the same collapse voltage, we find that the force is proportional to Tm squared times A to the 2/3 power with the same excitation voltage. So you can actually increase the force if you make the plate thicker. That has the disadvantage of reducing the bandwidth. I'll show you examples on that. So we have developed an electrical equivalent circuit with an accuracy at the finite element level, very, very accurate. And of course, because it's an analytic model, simulation time is very, very short. And we can handle absorbing boundary conditions easily due to analytic nature of the formulation. And also, because the simulation time is so short, it's good for design optimization rather than just verification. Let's first start with a single cell CMOT in water with a radius, say, a relatively big CMOT, 190 microns, and very, very thick plate. That would be this one. And then if you go down half in size and reduce the thickness, then you'll get this curve. And then if you reduce it further, as you see, the power output is also calibrated here. So you can see that the thicker ones will give higher powers. Now, our equivalent circuit, especially in the form of when you have an array, composed of these single electrical equivalent circuits of single CMOTs, many of them connected in parallel through an impedance matrix. Because the CMOT cells are actually not only coupled to the water by themselves, but they also coupled to each other through the water interface. So we really have a matrix, a full matrix, which takes care of the interactions, mutual interactions between them. To give you an idea what this mutual impedance looks like, the mutual impedance elements, so these are off-diagonal elements, it has a real part and an imaginary part. And the real part, as you see, does this oscillation, dying oscillation, but you can also see that the mutual radiation resistance has negative part. So you can actually get a negative resistance, a negative radiation resistance from the neighboring elements. And this is actually what makes the coupling interesting. Let's try to make a design example by, let's suppose we'd like to design a CMOT array about 760 by 760 microns. And let's suppose our frequency range that we like to use, so 3 dB bandwidth, let's say we want to do from 2 to 10 megahertz. This is pretty wide band. Let's first start with 3 by 3 CMOTs in this square of 760 by 760. 760 is, by the way, about it's about one wavelength at 2 megahertz. So you have to choose radius about 126 microns and thickness about 8 microns, and the separation between the cells are all kept at 3 microns. And when we simulate the frequency response of this array, we find that we operate at around 2 megahertz. The response drops. This is the power output of the array as a function of frequency. This blue curve shows for the single CMOT of the same size. When 9 of them, 3 by 3, 9 of them are put together, then the bandwidth expands. Of course, the power goes up. And there's a little bit of problem here. We'll be talking about that later. When you do 4 by 4, the same size, but 4 by 4, this time you have to use smaller radii and thinner cells, 5 microns rather than 20 microns. And when you do that, the bandwidth goes up a little bit, and still the problem here, the sort of a spurious resonance here, still there. When we do 5 by 5 in the same area, this time the radius is even lower, and the bandwidth gets better. You look at, in this case, the bandwidth is from 2 megahertz to 4 megahertz, 4.6 megahertz. If you do 6 by 6, then the bandwidth is this time from 2 megahertz to 5.4 megahertz. If you do 8 by 8, the bandwidth goes from 2 megahertz to 7 megahertz. And as you see, the spurious, what I call spurious resonances around here gets even more complicated when the array size gets bigger, when the number of cells gets bigger. We'll talk about these resonances later. And when you go to 10 by 10, 100 CMOTs, then we're getting there. The bandwidth is there. Now it's 2 to 9 megahertz. When you make it 12 by 12, now each one of the cells are smaller. Each one of the cells is about 30 microns and about 1.7 micron thick membranes. Then the bandwidth is really good, this time from 2 to 11.2 megahertz. But notice also that as you make each individual cell smaller, the power goes down slightly. So I'm going to make a comparison, 10 by 10 versus 11. So if you look at the comparison, the power goes down and the bandwidth goes up. Okay, so this is a comparison of these different CMOT designs. And right around there we have these spurious resonances, but the rest is very clean and very nice, very wide bandwidth. So our intermediate results are smaller CMOT cells give a better bandwidth at the expense of some reduction in power. There are spurious resonances around the resonance frequency of the individual CMOTs. The resonance frequency of a single CMOT should be selected below the frequency range of interest to avoid these spurious resonances. The excitation pulse should be high-pass filtered not to cause these ringings. So let's zoom in onto these spurious resonances. So these are the same cells, and around the frequency range, say at low frequency, relatively low frequency, is 1 to 1.5 megahertz. Actually, all the cells are designed so that these spurious resonances are falling in this frequency range, which is outside the band of interest. Now, if the spurious resonances are not well taken care of, there could be ringing in the impulse response. So if you excite the CMOT with an impulse, you can get some ringing, and these are visible experimentally. Well, let's talk about spurious oscillations. Why are they there? Can we avoid them? Can we make use of them? Or can we increase the Q factor of these resonances? To understand what these things are, let's start with just 3 CMOTs, linearly placed, equal size CMOTs, 3 of them. And if you plot the power output from these 3 CMOTs, this blue curve is just a single CMOT. You see it's like that. And when you put 3 CMOTs, and this M is a factor defining the separation. M equals 2 means they are just touching each other. If M equals 2, there is something there. If you separate them farther apart, this thing disappears. Now let's take a smaller CMOT and again do the same simulation. Single CMOT and 3 of them right next to each other with M equals 2 and further separated. When you see this little resonance in the response. And if you make even smaller CMOT cells, this resonance is even more dominant, a very high Q. And it occurs when they are very close to each other. When you separate them apart, the resonance disappears. So basically what happens is, these 3 CMOTs, and it may happen that the center CMOT actually moves in the opposite direction to the others, even though excitation pulls them, it goes up. Excitation is gone, it comes back. So it's sort of like negative resistance. So the central CMOT in this case sees a negative radiation resistance. So cells have low impedance near the resonance, and they prefer to push each other, if you like, rather than delivering power to the liquid medium. So they sort of pass the ball to each other at the resonance, and some cells see a negative mutual radiation resistance due to presence of the neighboring cells. Now, once we learned about these spurious resonances, we said, how can we improve the Q on this? So we optimized for these three CMOT cells, we optimized the distance between them. We saw that we can actually get a Q of 286 at some separation. Then we said, let's put three cells. V1 in the middle, so three symmetric cells located around them. In this case, Q actually, then we optimized the distance to get the highest Q, but actually the Q has dropped. Then we said, let's do it with 4. With 4, Q has gone up again to 149. With 5, Q has gone up to 153. With 1 plus 6 CMOT cells, Q is now 172. 1 plus 7, 205. 1 plus 8, 255. 1 plus 9, 324. And 1 plus 10, 363. So this is basically, there is one cell in the middle and there are 10 CMOT cells surrounding it at some optimized distance. When you do it further, then Q begins to drop again. So that is an optimal configuration. So cells with thinner plates give higher Q factors. It's possible to make the cells even smaller and get higher Q factors. We found that we can get Qs over 500 with optimized geometries. It's possible to optimize separation between the cells for a higher Q. So we're talking about CMOT cells in water, but they're moving vigorously, the center one, vigorously, essentially delivering no power to the liquid medium, but moving as if it's in vacuum. So locally, there's a lot of agitation in water, but nothing is delivered to the liquid medium as a real power. So we said, can we use this as a sensor? Because it is very sensitive to the local sound velocity and sound density, it turns out if you generate a high Q configuration and the resonance frequency is very sensitive to local variation of sound velocity and local variation of the liquid density. Suppose there is a cell nearby or something, so it can be used as an imaging tool. And this is a graph showing how this is the resonance frequency, normalized resonance frequency, how the resonance frequency changes as a function of density, of the local density of the water, and as a function of the local sound velocity. So there is a significant change in the resonance frequency, and if you have a high SNR system, you can easily detect very, very small changes in local density or local sound velocity. So to conclude, interactions between the cells of CMOT should be considered to avoid unexpected behavior, and pulse shaping is required for clean response, and spurious resonances can have very high Q values in optimized geometries, and the spurious resonances have the potential to be used as local velocity or density sensor. So our future work, we'll try to find CMOT array geometries that minimize spurious resonances, possibly by eliminating some of the cells. If you eliminate these vigorously moving cells which see negative resistance, we may be able to eliminate some of the resonances. And on the contrary, on the other side of the picture, we will try to find higher Q spurious resonances, and we will try to use this for a sensor application. Thank you for your attention.
Question?
So for the power comparison,
What was the input? How do you
Same input voltage,
Same voltage.
same collapse voltage. All cells have the same collapse voltage and all at the same input voltage. So these are relative, of course, not absolute, but relative to each other, it's correct. So if you use smaller cells, the power goes down slightly. We're talking about maybe 5 or 6 dB down. So if you use bigger cells, if you don't need the bandwidth, you have to use bigger cells, then you can deliver higher power. But typically you need wide bandwidth. So that is an optimization.
So are you suggesting using two different types, one to deliver high power and one to deliver very sensitive?
Yeah, if you're for example, for HIFO applications, where the bandwidth is not an issue, but power is the most important thing, then you need to use thicker plates, CMOS with thicker plates. With the same excitation voltage, you can get more power.
What kind of configuration do you see as being, do you have any preliminary design configurations that you see as optimal?
Well, just like the ones I showed, for example, if you look at the power like this, you know, this thing delivers over there, for example. Suppose we design this to work at 2 megahertz. We deliver here, let's say, minus 8 dB. Conventional design is somewhat similar to this. You know, you will get minus 12 dB. So we're talking about 4 dB additional power with the same excitation voltage. Of course, yeah.
Your excitation voltage is small as compared to the DC bias in this case?
It doesn't matter.
Like, I mean, if you swing
Yeah, it's independent. You can go all the way down. This is this shows only the linear portion of the picture, but the nonlinear portion it doesn't make any difference.
I was wondering, excuse me, what the effect is of the mechanical properties of the top plate. In other words, have you experimented with anything other than silicon?
Well, it's of course it's in the picture. If you use a stiffer material, then you can make it thinner for the same. But these factors all affect each other. So you can use a stiffer material, like some people are using diamond films. But then when you have a diamond film, it's very stiff. Then you have to make it thinner.
Is it only the effect of power, or it can be the effect that now for PCT transducers that can be surface waves and the structure of acoustic field can be a little bit different? This interaction between cells and surface waves.
Well, in the case of CMOS, because the CMOS are low impedance, we see these interactions especially around the resonance frequency. For the case of piezoelectrics, they have a much higher impedance. And for most piezoelectrics, this piezoelectric arrays, these interactions are not very important because, and not very significant. But these coupling between the array elements is for example, well-known problem in electromagnetic antenna arrays. You know, they have these electronically steered antenna arrays, especially military people have these things. And the antennas are coupled to each other, and some of the antennas see a negative resistance. So they have to put circulators at the output of every one to make sure that the amplifiers don't burn out. But I'm not sure whether I answered your question.
So what are you asking about interface
I'm
waves?
asking if acoustic field actually changes the structure. If you steer, for example, the focus, and even if you don't steer, if there's the phases of each element are different, if they communicate with each other, maybe they different.
Oh, you're asking whether the resonances here will move if you steer the wave. Is that what you're asking?
Where the acoustic field pattern.
No. So if you look at this, what he has, this picture, we actually have data for this, he doesn't remember, from 10, 15 years ago. The first solar electronics array we made had an identical feature to this. We had this resonance between 1 and 2 megahertz. We weren't sure what it was. We thought it was crosstalk. And those were 2D arrays, 128 by 128 elements. And we tested them at different frequencies, and the acceptance angle fit perfectly to theory as if you had plain piston mode operation. I think the biggest thing that I think Professor Atalar is raising with this is an ordered crystal in this plane. And that's what you're looking at. You're looking at omega K diagram for ordered crystal in the XY dimensions, not in the vertical dimension. But then when you take them all into a transducer element, like a 1D array element, the interface mode at that crosstalk, that is very similar to what you see in the pieces. Actually, in pieces it's higher than in the CMOS.
Actually, there was work from Vermont in France which showed actually the field from the CMOS, 1D CMOS array, and they did a comparison 1-to-1, was actually more ideal to a, similar to the ideal piston. So they were getting actually better near field even performance from a CMOS array as compared to piezo. I think that's the case where they're operating in the right region.
Well, you cannot get this kind of response from a piezo array. This goes all the way to
The
12.
guys are fighting out there. First of
No.
all, start up here, yes.
You can get even further down.
Yeah.
Very interesting also the sensing part. I was wondering, how do you distinguish between sound speed changes and density changes?
Unfortunately, they are coupled. We cannot separate them.
That's a classic sensor problem.
I have two questions. One, can you use CMOS to generate shear waves? And secondly, is there the equivalent of matching layers for CMOS?
I don't know if, no, shear waves, I don't know. Maybe Pierre.
Shear waves in water, you mean?
No, in tissues.
Oh.
In
No,
tissue.
just kidding. Shear waves in solids?
Yes.
The answer is yes. But we can pick it offline if you want, but the answer is yes. Because remember, when you apply an E field between two whatevers, there is force in there, and so there is locally force like an EMAT. You remember EMATs? And so an EMAT, it does the same thing. You get the force, the Lorentz force. And if you get the Lorentz force at different location with some periodicity, then you can send whatever energy you want phase in the CMOS itself sends energy in the substrate, it's longitudinal, because you're pulling on the bottom of the capacitor. And if you pull at it at different locations, you create an IDT effect. And then if you phase it properly, you can get that if you want to. And last one, and then we move on.
Just a quick comment.
Yes.
No problem with what you said about CMOS being low cross coupling and all this idea. But we produce the same result with piezo composite.
Which result?
In terms of generating beam patterns that are ideal.
That's not true. The people who, so we'll pick it up later, but I can tell you, people who have benchmarked side by side, like Hitachi, who sells them,
Yeah.
they sell piezos and CMOS. In terms of angular, lateral resolution for the same aperture with the same frequency, the same design, you get better lateral resolution with the CMOS than you do with the piezo. But that has to do with the acceptance angle change as a function of frequency.
Composite.
With what?
Composite. Piezo composite.
Even though.